Hello everyone, I'm Dhina Hari from IIT Roorkee. In this video, I'll be explaining to you about my project, which is image synthesis using stochastic differential equations. This is my CWS project for the course PHC 351 Fundamentals of AI/ML. Let's go right into the project. So now I'd like to give you an overview of whatever I've done in the project. The basic idea is that I give my model a rough sketch of something. In particular, it's a person's face, and the model gives me back a realistic image of a person constructed from the sketch that I gave it initially. Now we'll look into the details. I would like to explain you about something known as generative models. These generative models, what they do is they analyze data and they try to learn the probability distribution of this data. For example, consider images. Each image, for example, a 64 into 64 RGB image would have 12,288 pixels. So each image is nothing but a point in the high dimensional space, which is r power 1 22288, which means there will be a distribution for a class of images in this high dimensional space. The class of images, for example, could be the set of all faces, human faces I mean. The set of all human faces would be concentrated in a specific region in this high dimensional space. So we can find out the probability distribution of the set of human faces from this set of all images from this space. That's what generative models try to do. They try to approximate the true probability distribution of something and they try to replicate it. That's what I've written here. The subset of points that look like real faces actually form a very small structure region within this huge space, and hence we can find out the probability distribution of the true face distribution. These generative models, though they sound very advanced, they are actually advanced, but they are a little imperfect. Because we only try to approximate the true data distribution, but in doing so, we face many problems such as mode collapse, training instability, overfitting bias, and a lot of other problems. I'll explain you what these mean later, along with the details. Overfitting and bias, I hope you know what those mean. This leads to a new family of probabilistic generative models, which are diffusion models, which is actually the foundation of my entire project. Now let's look at what diffusion models mean. Diffusion models try to generate data by reversing a gradual noising process. In this project, I have implemented something known as differential editing. It's a method built on diffusion probabilistic models, which are a part of the deep generative model family. The main difference between this and generative models is the fact that I have used noise in these diffusion models. Actually use noise, which generative models do not do. And how this noise is used? They are characterized using stochastic differential equations. I'll explain in brief what stochastic differential equations mean in upcoming slides. So now let's go right into the project. So what I did in this project is I have used diffusion generative models and the mathematics of SDEs to perform image editing. As I said, I gave the image a rough sketch and I gave the model a rough sketch, and it finally would give me a proper realistic image constructed from it. I've just written whatever explained. It adds control noise to it, and then it runs a pre-trained reverse diffusion sample to reconstruct a realistic image that respects the input's core structure. Now I can, the final image that I would get from this would be much different from the initial sketch, or would be similar to the initial sketch depending on some parameters which I will explain in the code. So the goals of this project are to turn sketches into realistic images. The primary goal is actually to learn about diffusion models and to understand them, of course, and then the other goals are to visualize the forward and the reverse diffusion process, and also to provide a controllable trade-off between keeping the final output faithful to the initial sketch and making it as realistic as possible. So yes, as I said, first we will discuss a little bit about generative models, because our entire project is built on the fact that generative models are not very perfect when it comes to generating these kind of images. So I would like to explain about something known as generative adversarial networks. There are more generative models. For example, we have variational autoencoders. But in this presentation, I'll explain you about generative adversarial networks. They're known as GANs. They are a class of deep learning models used to generate new data that resembles a given data set, of course, by determining the probability distribution. What they do is they try to learn a model which is p theta of x. Theta, as you can guess, is obviously the parameter approximating the true probability distribution of the data, which you can consider as p data of x, so as to sample x. For example, as I've written, if we trained on thousands of face images, a GAN can find out the probability distribution of images which correspond to face images, and they can generate a completely new realistic looking face that does not belong to any real person. You can actually guess how generative models do it. As I explained, they find out the probability distribution. So any point in that region would correspond to a face according to this GAN. So it can just select a random point in the model which does not actually belong to any kind of real person. So yeah, generative adversarial networks consist of two parts, which are generator and discriminator. And the generator, what it does is it creates synthetic data. It takes a random vector, which is usually a Gaussian noise, and transforms it into an image g of z. Its primary goal is to actually form something which mimics a real face image as much as possible, so as to let the discriminator accept it as a real face image. Why? Because the discriminator is actually what decides whether or not the final output is a real image or not. It receives both real images from the training set and the fake images produced by the generator, and it tries to distinguish between them, and it can output a probability indicating whether whatever the output we have gotten is actually a real image, or it's some kind of image which does not actually resemble a real image face. Yes, earlier we had seen that the generative adversarial networks have problems such as mode collapse and training instability. We'll shortly now see why. It's actually formulated as a min-max optimization problem, because the generator tries to minimize this whole term, and the discriminator, it tries to maximize this. Finally, when we reach a middle ground in the both of them, the parameter which corresponds to the middle ground is actually chosen by the model. This is actually as I said, the generator tries to minimize it and to make d of g of z as close to 1 as possible, and d tries to maximize this objective. Why this leads to a problem? Because you see, there is something known as training instability. G and D are trained in opposition because, as I explained, G tries to minimize it and D tries to maximize it. Small changes in one of them can destabilize the other function completely. The training can oscillate or fail to converge. We might not actually obtain a middle ground, and this will obviously lead to instability, and we'll not be able to train the model. There is something known as mode collapse. This happens when the generator only produces a few varieties of samples, ignoring other possible outputs. For example, what might happen is it might always generate similar phases. The probability distribution might be on a very small area, and every phase we might get might be the same phase or similar phases, which means the model has actually failed. Also, these generative adversarial networks do not actually give us the probability distribution of the data. What I mean is, we cannot find out whether the image we have gotten is similar to a phase or not. I mean, we cannot get the number. We cannot get an explicit number which tells us whether or not this is similar to a real phase. This is also a very big disadvantage, I would say. And that's exactly the reason behind why I use diffusion models in this project. What these diffusion models do is they add and then remove noise from an image. This allows the model to start from a sketch or a rough image. We can add a controlled amount of noise to it and then gradually denoise it into a realistic image. The process of adding noise, as I explained earlier, is what separates these from generative models. As you can see, these are better than GANs because this is step by step and this is more predictable, and we can control it easily, unlike generative models in which the probability distribution is found out by the model itself. So let's move into the project now. I would just like to show you the code as well a little bit. So yes, in the first cell, all I've done is I've not done much. I've just imported the libraries and I've created the directory, and I tried to check whether or not GPU is available, and that's what I've done in the first cell. Now let's go back to the diffusion models, which is the main focus of this project. So as I explained, what a diffusion model does is it tries to reverse a gradual noising process. You can see x0, x1 till xt here, right? What these x represent is the state or the state of the image at that point. x0 refers to the initial state of the image. For example, if I give it a sketch initially, that initial sketch is x0. xt is the final state of the image, or finally how the image looks like after I have gone through t iterations after adding noise for t times, is what xt means. And then now we use something known as unit. What this unit architecture does is it tries to predict the steps backwards. That is, we first add noise to it and then we denoise it to obtain back the original image, which will now look realistic. The name, why we call it unit, is because you can see how this goes in a U-shaped manner. First we have our image, and then we try to noise it, and then we try to denoise it and then obtain the original image back. That's loosely the reason behind why it's known as unit. There are other reasons which I'll explain to you in the end of this presentation. So in the forward process, noise is gradually added to the image. This is x subscript 0, which is the real data, over t steps to obtain a sequence of increasingly noisy images. The forward diffusion process is modeled as a Markov chain actually, in which noise is gradually added to the clean image. It is expressed as you can see, this is n means the normal distribution, and xt means the state of the image at that point, and this I is the identity matrix. This notation actually means this beta ti is actually the covariance matrix of this normal distribution. It's a multivariate normal distribution. This is how multivariate normal distributions are usually represented. This is the covariance matrix. I'll explain you about these in the next slide. x0 is the original clean image, which is the input sketch or the sketch that I first give to the model. xt is the noisy image obtained after t diffusion steps, as I explained. Beta t is a variance parameter controlling the amount of Gaussian noise added at each step. Why we do not add the same amount of noise at each step is actually because initially what we would like to do in the noising process, we would like to add as much noise as possible. But if it has already become too noisy, we should stop adding noise as much as we did in the initial stages of the noising process. This is because we do not want to obtain only noise in the end. We want to obtain something from which we can denoise to obtain the original image. The I is the covariance matrix, as I said. Our goal is to train a neural network that reverses this process, transforming the pure noise back into a meaningful image, a realistic phase in this project actually. Yes, the reverse process is modeled by this, in which theta is the parameter. The n, as I explained, is the normal distribution, multivariate normal distribution. The unit architecture tries to predict the noise component, which is e theta, added to the image at each time step t, because if it is able to detect the noise architecture, it will be able to denoise the image back to its original form. And yeah, it varies from t to t. You can think of t as time or time step actually. Yeah, it's different from each t for reasons I explained earlier. So in this project, I actually have used a DDPM model. What this model, it's a pre-trained model actually. It defines a discrete approximation of the stochastic differential equation. This DDPM model is actually trained on a celeb A dataset, which contains the faces of many celebrities. It's trained on it already. Then what happens is that the unit tries to denoise the noise image carefully, producing a new image that is realistic as well as faithful to the virtual image. Yeah. Now we'll look into the stochastic differential equations, defining or the differential equations that actually influence our project. Yes, so what stochastic differential equations mean? Differential equations, as you can guess, they are just, you see this term here. If we do not have this term, we'll get something known as a differential equation. But since we have this term, we get a differential equation, stochastic differential equation. Stochastic just means probabilistic. This term is actually a noise term, which is added to this, and this noise term varies for each time step t. X is actually the data, which is the image that we, the input image. F of x comma t is the deterministic part of diffusion, because this part never changes, and for that reason we call it deterministic. We can determine what the value of this function is at all times. G of t is the diffusion coefficient, which controls the noise intensity, and Wt is the standard linear process, Brownian, which models the Brownian motion. This term is actually the intensity of the noise, which changes for every time step t, and this is between -1 and 1. It's from the normal distribution actually. But this is a continuous stochastic differential equation. How you actually do them in real life or in the code is actually you discretize them, because of course you can't use continuous equations as such. So we discretize them and then we use them. So how they are discretized, as you can see, this is the normal distribution, and this is our state of the image at time t, and this beta t, as we have already seen what this is previously, with this noise parameter at time t, and this is the covariance matrix, and the marginal distribution, which is q of xt given x naught, it's equal to this, where alpha t is equal to 1 minus beta t. What this alpha bar t means is it takes the product of all alpha i's before t It's known as a cumulative product. I'll also explain this in the code. I is the identity matrix, as I've already explained. So what the unit learns, as I said, is actually the reversing process, which is given by p theta of x t minus 1 given xt, which is also given by a normal distribution, for which this is the covariance matrix, and the mean term of this is predicted using the neural network, which is the unit, and that's given by this term, as you can see. We've also used this in our code. I'll explain you this when we look at the code next. As I explained, alpha t is nothing but 1 minus beta t, where beta t is our variance schedule parameter controlling how much Gaussian noise is added at each step, and alpha bar t is just the cumulative product. Why we use the cumulative product, we'll look into that later. So we obviously have a loss function in this, which is just a predictor of the how much whether or not our output actually matches a realistic image. It's given by this term, and this term trains the model to correctly estimate the noise that was added to the clean image in the neural network actually. Now let's look at what happens in the noising process. First, we partially diffuse an input image, which is a sketch that I initially give to the model, and then we try to run the reverse process with the guidance to refine it. So xt is given by this term, and then we denoise it step by step, iterating it through every value of t. As we saw, the mean value is given by this term, so we use that term to find out the previous states of the images, which is given by xt minus 1, and we do it till x0, but we also add the Gaussian noise term in this, as you can see. Yes, this slide is added once again. Now I'll explain you a little bit of the code actually. This is the code for modeling the stochastic differential equations. First we make the first I just import the necessary libraries, torch.nns neural networks, the library of torch used for neural networks, and PIL is Python imaging library. I define something known as a beta schedule. What it does is it's a linear schedule of noise levels from start to end over t time steps. As I explained earlier, the amount of noise added at each step is not actually the same, and beta t is the term which actually determines the amount of noise that's added to the image at each step. We create the beta schedule using this function. We linearly increase beta t so as to control how much noise is added at each step. Then we define a class known as the diffusion helper. The betas are created using the beta scheduler function, which we defined earlier, and alphas represent how much to keep at time step t, as I've explained, as alpha t is equal to 1 minus beta t, and the cumulative product, which is the alpha bar t, it tries to it's the product of all alpha values up to step t. It represents the total signal in the sense the noise term, which is remaining after t noise steps. Then you can see the Q sample. If noise is none, noise equals torch dot and then like x naught. What this actually does is, if no noise is provided, it actually selects Gaussian noise and it adds it to the input, and then it gets the cumulative product for the given time step and returns both the noisy image and the noise used. Yeah, that's what it does. And then you can see piece sample. What this does is it samples the reverse distribution and it gets the distribution parameters, and then in the final step it returns the mean. The mean is what we saw here earlier. This is predicted using the neural network, and I'll explain the code for the neural network later. And then it runs the load image tensor. It converts the loads an image and then converts it to a tensor, and then as you can see, it then converts it to -1, 1, a value between -1 and 1, and then it converts it back to that converts the image back, is what this does. This is the code for detecting the unit parameters. Now let's go back to the presentation. Yes, so this is the most interesting part of the project, I would say, because this explains about the image synthesis. Instead of generating the image from scratch, we start from the sketch I have done from various sources. The noise level determines how much of the original image's structure and content is retained. And by controlling this balance, we can perform tasks such as turning a rough sketch into a realistic image while being faithful to the original sketch. As I explained earlier, the pre-trained EDPM model is trained on the celeb A dataset. It has the faces of many celebrities. Each iteration of the denoising process, it can be visualized as the model imaging increasingly detailed and natural versions of the face that are consistent with the initial sketch. This process balances stochastic creativity and deterministic reconstruction, making this an effective method for structure-preserving image synthesis. This is what I just explained in the earlier slides. These are the inputs that I gave to my model. This is a rough sketch. All of these are rough sketches that I have done from the internet. Now let's look at the outputs of these rough sketches. Let us first look at this. What happened here is I gave a sketch. It was noised first, and then the unit tried to denoise it, and finally it obtains something close to a human face. As you can see clearly, it's very close to a human face, and this is the image I obtained from giving the model this image as a reference image or sketch. As you can see, it's also very close to a human face. And then this is the one I got from using this sketch. These 4 are images I got from using other sketches. The final output consists of, it's not very high quality images because the size of the images is very small. We are zooming it in, so the quality reduces a lot. These appear not very natural, but they appear like a human face. All these images, they look almost like human faces. This looks a bit different. And I would also say this image, let's just wait for a few seconds, is very close to a human image. The process can be repeated as many times as we want to produce many samples of images from the same sketch. The reason behind this is actually that our model is stochastic. What stochastic means is it's exactly the opposite of deterministic. If you give the same parameters to the model again, it is probably going to give you a different output. And that's the essence of stochastic differential equations, I would say, stochastic models for that matter. Yes, now let's look at the code that explains the process of image synthesis. These are for detecting the unit parameters. Yeah, this is the code for image synthesis. In the beginning I have just imported the necessary libraries and nothing much actually here. I've created these directories in earlier codes, which I'll explain you after this. This is the path for my pre-trained model. I defined it, and then I defined the path for my sketch and the path for my output directory. The number of samples refer to the number of images that I wish to get from the model. The interim time is something that tells the model how much to actually modify the output as compared to the initial input. So this value is actually 0.4 in my code, which means I modify it to a medium level, not too much, not too less. It's just medium, actually less than medium, I would say. If this value is too less, what might happen is we might get some image which is very close to the sketch and might not actually look realistic at all. And if this value is too high, our final image will look nothing like the initial sketch, but it will be very realistic. Image size is just the pixels of the image. Then I create the directory for this is just to check whether or not I'm using the CPU or the GPU, and this is just to make the output directory. This imports the diffusion helper class, which we defined earlier and saw earlier, with 1,000 time steps. As we saw earlier, there are time steps actually. From 0 to t. In our model, t is equal to 1,000. That's why that's the parameter we have defined here. Let's go back to the image synthesis. Yes. First, what we do is we load the image, and then we convert the image to something between -1 and 1, and then we calculate the diffusion step, and then we ensure that the step is within the valid range. Then what we do is the generation loop, which generates multiple outputs from the same input, because all of the output we get from one single image is actually not the same. We get different outputs, as I explained earlier. And this is the loop to, as you can see, for I in range number samples, and our number of samples is 4. Num samples is 4. So this will generate 4 images. All these processes I have already explained you. This is the forward noising. This is the forward noising which I explained here. Yes, this is the forward noising, and this is the reverse noising. It does those processes, and then it saves the final image after creating the full path. That's what the code for image synthesis actually does. And this is just to view the results. I imported the libraries required, and then from Python imaging library I imported image, and I have just defined the output directory, and then I have tried to plot the images. These are images I got from earlier iterations. These are not very realistic actually, because I used a lesser interim time for these images. That's why I got a different output. This was from a different input actually, and this is the code to generate the GIF image. I'll explain this to you after explaining the unit, which is the heart of the project, I would say. Yes, unit. So this is very interesting and the important part of the project, I would say. Unit is a convolutional neural network. It was developed for image segmentation. I would just like to show you the a schematic of a unit. As you can see, there is an input image tile. What this unit does is, it reduces the pixels in every image and increases the features. It extracts the features. It keeps extracting the features and it reduces the pixels a lot. Then, from the extracted features, it tries to reconstruct the image. That is basically what the unit does. There is no actual abbreviation for unit. This is named unit because, as you can see, it's like a U. It's U-shaped actually. The architecture, if you think about it, it's first pixels and features, and then it reduces the pixels and extracts more and more features, and then from the features it constructs the pixels back. That's why it's called as unit. Now, yes, these are all things I just explained now. During the contraction, the spatial information is reduced while the feature information is increased. The expansive pathway combines the feature and spatial information through a sequence of up convolutions and concatenations with high resolution features from the contracting path. This is just a fancy way of explaining whatever I said now. Yes. Now let's look into the architecture of unit. So yes, this is the architecture of unit. I first just imported the modules, necessary modules. I imported torch, and from torch I imported the neural network module. I imported this functional. Functional is just to define a function that doesn't hold any parameters. And then of course I imported the math module. Then I defined a class known as swish. Swish is actually a popular activation function. Now, what are activation functions? These calculate the output of a node based on the input and weights. These determine whether a neuron have to be fired or not in a neural network. What I mean is, a node might not be activated. How it's activated is actually with the help of the activation function. It will tell us whether or not to activate the node. Swish is defined as x times sigma of x, where sigma of x, it's a sigmoid function. It's 1 by 1 plus e power minus x. And you can see if the value of x is too high, let us say, not very high, if the value of x is just positive, then sigma of x will be something close to 1. It will be very close to 1. It will not be much different from 1. And since we multiply x with sigma of x, if x is positive, the value of this activation function will be x itself. If the value of x is negative, then the value of sigma of x will probably shoot up. It will become too high, and the value of the activation function will become 0, which means the neuron will not be fired. As I said, the activation function is a gate that determines whether or not the neuron should be activated or not. Yeah, these are mathematical operations, obviously. For positive output, you get the same output. It's like an identity function, just like I mentioned earlier. For negative x, we get the output 0, and it doesn't exactly approach 0. It mostly approaches 0, because if x is because this function is actually smooth, and at x equals 0, we get 0. Because although sigma of x is equal to will become 1 when x is 0, the swish function also gets multiplied by x, due to which it becomes 0. The sigmoid part acts as an attention mechanism. as I explained, it tells us how important this particular feature is. X is the feature we are talking about, and sigma of x tells us whether or not this feature is important. The multiplication, it acts as a strength control. How strongly should this be expressed actually? Because this tells us whether or not something must be added, and this tells us if something is added, how much should it be added, the feature. Now going back to the unit architecture, this class known as time embedding. The max len tells us the maximum number of diffusion steps in our model, and this D model is the dimension of the embedding space. This just ensures that our dimensions are even, because half of them would be assigned to sine and half of them would be assigned to cosine. So we want them to be even. This is just to ensure that. Then we initialize our class, and then we define other functions. For example, this is just to create an array, a geometrically decreasing array of frequencies, normalizes decreasing frequencies exponentially. That's what actually happens here, because the amount of noise we add to a model in each step, it's not the same. We have to decrease them, even geometry. We have to decrease them in each step. Why I'm telling this is because let's go back to this GIF image. As you can see, the GIF slowly refines into an actual person. First, the noise added is very high, and the amount of noise added gets lower and lower. And in the refinement process, the amount of noise added becomes very less. And why? And for this to happen, we have to define the noise, the added noises, in such a way that we keep them decreasing geometrically. That's what this does. Torch.arrange 0 T model step 2, and we divide it with itself to normalize it, and then we multiply it with this function, and then we decrease it exponentially. This is the position of the array for the 1000 diffusion steps. We defined it earlier, the number of diffusion steps per 1000. This embedding, this is just to know in which stage of editing we are on. In the early stages, we need to focus on the big shapes, I would say. That's just what I explained just now. And in the refinement process, we need to just focus on the smaller shapes. We need to add noise slowly. And in the last step, we just have to, the model just has to polish the image. Yes, that's it. Now let's go back to the presentation. Yes, this is downsampling. Downsampling is what I explained earlier. This process is actually known as downsampling, reducing the pixels and increasing the features. What we do in this is, first we initialize the class, and then we create a 2D convolution layer. This 3 here means we use a 3 by 3 filter or kernel to look at pixels. Straight to it. It means move the filter 2 pixels at a time instead of 1, so as to make the output half the size, because this is downsampling. We are reducing the amount of pixels. The padding is just to add 1 pixel border around the image so that the edges not get ignored. These are generic terms which are used in any convolutional neural network. Then we have to look at the upsampling. This is used for clean upscaling, and then we refine the image in an intelligent manner, as I have written. We try to obtain the image back from its features without the pixels. We try to reconstruct the pixels. That's what upsampling does. It takes our image and it makes it 2 times wider and 2 times smaller, and it uses the nearest neighbor method actually for this, and then it will return us a bigger but blocky version, in the sense it will not be very clear actually, because we are reconstructing the pixels from the features. That's what this does. This interpolate function basically does that. It returns us a bigger version of the image. Now let's go back to the code, and yes, this is the attention block. This is also a very important block in the unit. It normalizes features across a group of channels, and here we have used 32 group size. Why 32? It's because it's just for stable gradient flow, I would say. It's to normalize the input tensor, and it's for better stability of the model. Yes, it helps the network to stabilize gradients and improve convergence. The attention block helps the diffusion model capture long-range dependencies in an image. Basically, it reshapes for attention computation. It computes the attention weights, and that's what this attention block basically does. These are the attributes of this class object. This learns how to extract, which is what each pixel wants to know, and what are the features in each pixel is defined by this, and the value of each pixel is learned by this, and finally we define something known as the group norm, which is given by this term. B is the batch size, C is the number of channels, and these are the spatial dimensions of the feature map. We have defined them here. We have used them here. In diffusion models, as I explained earlier, the unit is actually the denoising network. It takes an input, which is the noisy image, xt, which is the image we obtain from the noising process, after the noising process, and the diffusion time step t, so as to understand how much noise we have actually given it, and then it tries to do the denoising process. These are the equations governing the denoising process, as we already saw them earlier. Alpha bar t, this is just the cumulative product of all the values of alpha. Alpha, as I explained earlier, is equal to 1 minus beta t. I is the identity matrix, and this is the covariance matrix of the entire multivariate Gaussian. This is the reverse denoising process. It just tries to reiterate everything back to the original image, which in our case is the realistic image. After the upsampling, the network outputs a tensor with the same size as the input image. The output represents the predicted noise E theta of xt, t, which we actually used in our model, which is then used by the diffusion model to gradually reverse the noising process, so as to obtain the realistic image back. Yeah, this is something I already showed you earlier. Let's go back to the code. Yes. This is the rest block, class rest block. This is first of all, let me explain a little more details in this. This is to reshape our attention computation. This softmax converts the weights into probabilities, and then we finally project this using self.project. Now let's go back to the code. This class, what it actually does is it combines residual learning and temporal conditioning and the normalization actually. TDIM is the time step embedding dimensions, and this ATTN means attention block. This is to activate the our activation function, which I described earlier. This is the time embedding projection. It's to determine the non-linearity of the activation function. And this is the group norm that I defined earlier in the presentation. This is the group norm, and we use that here in this class. This helps us to this is just to use attention block if this is true, or else it will use the same input which is given by n dot identity. And then we are going to define the forward function, which tries to do the entire iteration process and then gives us the output. Now let's look at the this is just a one-by-one convolution actually, by the way. If the output convolution is not if the input and output are not equal. Yes, this is the code for the unit model actually. Here we initialize the class, and then the channels are multiplied by 4 for the time embedding dimensions. In the end, we actually obtain a noisy image. From the noisy image, we obtain the clean image. That's what we do here. This is the forward block which we already used in various other codes. For example, forward function was also used here, also here, also here as well, obviously. We loop through multiple channel multipliers for each I in this function actually, and we increase the channels by mult, which we defined earlier, and then we add multiple rest blocks, which is which we already defined earlier. This also ensures that all attention indices are within the valid indices of the unit input convolution, and it converts the input image to the base feature space, and then we do the downsampling, which is done by this. And finally we return x, which is our actual output of the unit. So yeah, this is the architecture as I explained earlier. The final input we obtained, as I showed earlier, are this. You can see how the noisy image actually becomes a clear image from these GIF files. This in particular, I would say, is very close to a real person's face. The input I gave to it was this, I believe. So that's it actually. Now let's just look at a small summary of the entire project. Obviously this fully demonstrates the application of diffusion-based generative modeling for image synthesis. We used a denoising diffusion probabilistic model, which is DDPM, which is a pre-trained model trained on a celeb A dataset, and we used a unit denoising network. The model becomes capable of transforming a rough or a noisy input, which is a sketch here, into a high quality image. Not high quality, but a realistic image. Unlike the traditional models, these diffusion models rely on a probabilistic framework, which refines our images through a sequence of noise removal steps. Overall, I would say this project actually tells a lot about the importance of stochastic differential equations in the process of diffusion models. It's very robust, and it can help us interpret diffusion models in a better way, and we can also use this as a foundation for advanced image editing, restoration, and creative synthesis. One example I can think of is for example, we can obtain real images from a sketch that we drew by our hand. It will be really cool actually to just think about it. Yes, that's it. These are the references I have used for the project. Thank you.